Hear ye, hear ye. Good afternoon, everyone. Good afternoon. It is nice to see all of your smiling faces. Jesse's like, you don't have to talk that loud. So thank you all very much. All right, let's get to the talks. You did not come here to see me. Our first talk is going to be by Dr. M.Harbour. Dr. Harbour is a staff engineer in the Dayton Engineering Advanced Projects Lab of the Defense and Intelligence Solutions Division. He's a subject matter expert in artificial intelligence, machine learning, human autonomy teaming, neuroscience, electrical and computer engineering, avionics, unmanned aerial systems, and autonomous vehicles. Stephen leads and performs ongoing basic and applied research projects, including the development of third-generation spiking neural networks and neuromorphic applications to include both hardware and software. He is a former United States Air Force test pilot with over 5,000 flying hours and a number of aircraft, to include the F-16, B-52, and EC-135, among others. Stephen earned his BS in electrical engineering from Mississippi State University, his MS in aerospace engineering from Embry-Riddle Aeronautical University, and his PhD in neuroscience from North Central University. Originally from Fort Worth, Texas, 3 things you might not know about Stephen. His motto is integrity first, service before self, and excellence in all we do. Rings really familiar from the Air Force. Great values. His hobbies include teaching, computer works, and working on cars. And he is all about family, country, mentoring, giving back, and Southwest Research Institute. Please give a warm Tom Talks welcome to Dr. M.Harbour.
Good afternoon, everybody. Can everybody hear me? Pretty much? Pretty good? Gentlemen, thank you so much for coming. I really appreciate that. I'm M.Harbour, and I'm going to talk about neuromorphic engineering and advanced computing. We've already talked about me, so that saves time. This is the research team in Dayton, Ohio. And we have, as you can see, a couple of openings. All these people there make what we do happen. I'm surrounded and blessed by these fine, talented individuals. We have a couple open positions in Dayton, and I think we're going to start also getting some neuromorphic positions here at San Antonio as well. So we're planning that too. So you might be interested. So I'll sort of use it as a recruiting media here. And we get home support from here. We have Ken Holliday and others that also provide support when we need it. Okay, what's the problem? Why do I care about neuromorphic technology, right? Well, GPUs, that's where it's at. Whoa, I'm getting all kind of, do I need to turn the mic off? You got it? GPU, just give me more GPUs, right? Well, GPU servers, you probably don't realize this, but GPU servers, especially if they're processing GP-3 type processes at these server farms, and there's quite many of them across the country, they produce as much CO2 as 1,300 cars in 2 weeks. Bet you didn't know that. That's something we got to fix. So more GPUs is not the answer. We have to find some alternative in order to continue to process as well as they do and perform as well as they do. What's a solution? Well, we need to find a processor that performs as well to better than the GPU, uses a lot less power, and a lot less energy, right? And so you see I'll try the pointer here. You see the little hand-drawn sketch there. That's where neuromorphic processors lie. We've been testing these suckers for, I guess, upwards of 3+ years, and they perform as well to better than GPUs for a lot less power usage. Okay? Low He2, for example, very low power consumption with better performance than a GPU. Well, what is neuromorphic technology, and this funny name, what does it mean? Well, it involves neuroscience, the human brain, neurons, and it also involves electrical and computer engineering. So basically, we model a processor, if you will, as though it's like the human brain. And so I'll go into some neuroscience type stuff and explain that a little bit better. But we decided as a community, if we mimic the human brain, maybe we can do more things and use less energy while we're doing it. It so happens that our brains, consume about 20 watts. The light bulbs in this room pull more power than that. And they're very good at reasoning, very good at reasoning. In fact, they're better at reasoning than any computer we have today. 4 bananas a day is all your brain needs. Okay? Not much. The body needs a lot more. And from that, our brains have neurons that use synapse and also spiking neural networks. So when a certain voltage threshold is reached for a specific reason, it will spike and pass on that message to the next neuron. And so we model that artificially. And we're finding orders of magnitude less power usage, and pretty much in everything that we've tested exceeds the performance of the GPU. And so it's event-based processing for those that are in architecture. If I know I'm in architecture, happens all the time. It has memory that's off the main processor, so you have to go off the processor to do memory. But we don't have a memory process, a separate location in our brains. It's all happening in our brain globally, right? And so we do the same thing with a neuromorphic processor. The memory is on the processor. You don't have to go off-board for memory. That saves time, and it saves energy as well. The information is encoded in spikes, just like our brain is. And I'm going to use the pointer again, I think, or try to anyway. There is, so there's the spike, if you will. Hits a threshold, yep, minus 70 millivolts, spikes, comes back down, and the message is sent. It reinforces that if it gets another spike into the following neuron really rapidly, and that causes long-term potentiation, which is memory. We do the same thing electronically and through software. So we've made a silicon brain, if you will. Now, when I say that, it's not like as powerful as a human brain on a processor, okay? It's not even close to it. But it's a start and being able to save energy and have better performance than a GPU. And what you see here are some models, and it's quite fascinating, actually. So the leaky integrate and fire, the leaky integrate and fire model, and you see these right here, that's potassium, right, and sodium. This is happening naturally in our brains, and there's there's a barrier between the cell wall and the fluid, and you get basically the ionic, try and explain it. You get an ion exchange. You have the leaky integrate and fire model, so you have the leak, which happens with the constant resistance, and then you can vary the resistances on the other two channels to get your spike when it's necessary. And this is happening naturally in our brains. The other two models are another way to do it. And here's some proof that we've done actually here at Southwest Research that substantiates what we found. And it's pretty amazing. Those of you that are into machine learning, for example, you guys are familiar with the CFAR 100 data set. It's an image recognition data set. It's rather complicated. It's labor intensive. And with very few epochs, we compared it to a CPU and one of NVIDIA's better GPUs with a neuromorphic processor, and the neuromorphic processor's accuracy with that minimal a number of epochs was way better. And the numbers are shown in the chart, as well as in 6 milliseconds it reaches inference with that low amount of training and is more accurate. I believe at 85% at that point, when the other two are around 35% with that low amount of epoch. So it requires a lot less training, and it's faster, and it reaches an inference much quicker, and the accuracy is better. And pretty much we think it's a no-brainer to go over to a neuromorphic processor. And then this shows some power usage, 32 milliwatts versus, say, 1,355 milliwatts, for example, with an FPGA. We had a project called BATSLAM, and BATSLAM is just that. So some of y'all might be familiar with simultaneous localization and mapping. We do it as humans. Everyone doesn't rely on their Google phones, or maybe everybody does, but the hippocampus of our brain does the mapping of our area, right? We learn in there. Also, we have neurogenesis that occurs as well. So, well, bats do the same thing. Bats don't fly great distances with echolocation. They do that with three-dimensional SLAM, like we would do it. Simultaneous localization and mapping. They do it very effectively. I believe here the Mexican free-tailed bat is at one of the caves. I think it's Bracken Cave, I think. And they go 100 miles or so, and they know where they're going. They come back. They can go different ways and come back directly. They attack prey with echolocation, but they travel high velocities, and they use SLAM with their hippocampus. So we modeled that on a neuromorphic processor for our drone, for our test drone, and we were able to successfully have a 97.2% success rate in navigating to the target on the true path versus the path that it chose to get there, which is pretty amazing. And it did this with path integration, which is vector calculus. It did not use GPS. It did not use, at this point in time, it did not use any camera information. So it was all internal. Bats see very poorly. So in a GPS denied environment with low visual cues, you can theoretically navigate with this system, which we were very impressed with. This is published. I think it's about to enter IEEE Explorer within a week or so. And it was presented at a conference and won Best of Session. And there's a bat. I think the next one's going to be the drone footage of some of the testing that we did with the drone. And I will talk to it as it flies. So it starts in a predetermined, it's initiated with the position where it knows it's at. So it knows those coordinates. And then we had it fly to a couple of different points on its own using the path integration. We had the GPS on to be able to compare, is it going where it's supposed to go versus where did it really go? And it's going to basically go to the left about 10 feet or so, and then eventually stop. Then it's going to return and drop in altitude about 16 inches here in a moment, and then return back to where it was, and then stop. And all using the neuromorphic processor and no other sensors to do that. And we're taking this further. We're doing further research with this, using the next level, the next generation of stuff that we were procuring. That concludes my TED Talk. Or Tom Talk.
Thank you. Excuse me. Fantastic. Wow. A lot of people don't realize the work that goes on at our off-site campuses. And the campus in Ohio is one of the newer ones, but I always encourage people as you're traveling around the country doing these different things. Some people go to Ohio because that's where they're from and they go home. Visit the off-site offices. Stop by there. They'd love to see you. They invite you in, and they'd love to show you the work that they're doing. So if you get the opportunity, please do that. And you can get by on 4 bananas, which is kind of cool. All right, we're going to continue on.